the envelope theorem that we gave in the beginning of this week apply to equality constraints. Then of course the next question you will ask is, are there any envelope theorem for inequality constraint? The answer is yes, okay? But to be honest, if you think over it, it shouldn't make any difference. Why? Because if you have an inequality constraint, for example, h of x1 up to xn less than or equal to b, okay? Then at a maximizer, there are two situations, right? Either the inequality constraint is binding. If it's binding, what does it mean? That means that the maximizer will give you equality. So in this case, you can treat the constraint as equality. Right? Because if it's binding, that means by definition, the maximizer will give you equality. So you can really treat the constraint as the usual equality constraint. How about when it's not binding? If it's not binding, last week we mentioned that when it's not binding, the corresponding Lagrange multiplier, lambda, equals to 0. Therefore, the constraint will disappear from the Lagrangian. So we can ignore it, okay? Okay? So when you have an inequality constraint, either you can ignore it when it's not binding, or when it's binding, you can treat it as equality constraint. That's why for envelope theorem, you really just have the version for equality constraint. And okay, so this theorem, although I make it sound like a separate theorem, but actually the entire conclusion is identical to the case with equality constraint. So in other words, there is no new theorem at all, okay? So we still have differentiating the maximum value function with respect to a parameter equals to the partial derivative of the Lagrangian with respect to the parameter by evaluated at your maximizer. Okay, let's do an example. So, example. Find the maximum value of this objective function x squared plus x plus 4y squared subject to three inequality constraints 2x plus 2y less than or equal to 1, x greater than or equal to 0, y greater than or equal to 0. Actually, this is a question from your homework. So this is actually from homework 12, question 3. Okay? So I just remind you the key step. So one of the key steps is the Lagrangian, in this case, is the objective function. And then you have three inequality constraints. That's why you need three Lagrange multiplier. So minus lambda 1 times, okay, the first inequality gives you the function 2x plus 2y minus 1. And then don't forget, you have to rewrite this two inequality as minus x less than or equal to 0 and minus y less than or equal to 0. So you get minus lambda 2 minus x and minus lambda 3 minus y. Okay? And then in homework 12, question 3, we find that, okay, a maximizer, the maximizer is given by xy lambda 1, lambda 2, lambda 3 equals to 0, half, 2, 3, 0. And then the maximum value equals to 1. Okay? So I didn't do it instantly, but check the homework question. Then you will get the answer. Okay? But the part that I want to do it with you is the second part. That is using A and the envelope theorem to estimate the maximum value of this time, the objective function is changed. Instead of 4 here, it becomes 4.1, but then the constraint is unchanged. Okay? So there's only one parameter that changed, is the coefficient of y squared. So we do the usual thing. We firstly formulate the optimization problem in parameterized form. So we want to maximize the function f equals to x squared plus x plus this is a parameter, so alpha, or maybe I call it a0 as usual, a0 y squared, and then subject to the constraint is unchanged, so 2x plus 2y less than or equal to 1, x greater than or equal to 0, y greater than or equal to 0. Okay? And then what is the Lagrangian? So the Lagrangian would be x squared plus x plus a0 y squared minus lambda 1 and then 2x plus 2y minus 1 and minus lambda 2 minus x minus lambda 3 minus y. And then for different choice of alpha 0 here, you get a different maximum value. So we let f max equals to the maximum value with parameter equals to alpha. For different alpha, you get different maximum value. So this is a function not alpha, sorry. I remember the previous notation. So a0, so it depends on a0. For different choice of a0, you get different maximum value. Okay, so then how do we estimate the new maximum value? So we want to, by linearization, f max, so we want to estimate when a0 equals to 4.1. And this approximately equals to f max at the given initial parameter is 4, and plus differentiating the maximum value function with respect to your parameter evaluated at your initial parameter and times 4.1 minus 4. So this is how you do linearization. And now you just need to figure out what are this, okay? What are this? So in particular, to calculate the derivative, we're going to use the envelope theorem. So note, the df max dA0 when A0 equals to 4 by the envelope theorem, so let me call it EV, that equals to differentiating the Lagrangian with respect to your parameter and evaluated at your maximizer. But now you're interested when A0 is 4, so you're trying to put in the maximizer when A0 equals to 4. Okay? So let's do it step by step. Differentiating L with respect to A0, so L is here. Differentiating with respect to A0, I get y squared. So this is just y squared. Evaluated at the maximizer for when the parameter is 4. So according to part A, the maximizer when the parameter is 4 is given here. So 0, half, 2, 3, 0. So in particular, x, y, so y is here. So y squared would become a quarter. Okay? And then, so, hence, f max 4.1 is approximately equals to, what is the maximum value when the parameter is 4? Well, when the parameter is 4, the maximum value is 1. So this is 1. So this is f max when the parameter is 4. And the plus a quarter, this from the envelope theorem. And at times 4.1 minus 4. So at the end, when you simplify it, you get 41 over 40. So this is approximately the new maximum value when you change the parameter of your objective function to 4.1. So that's it.